Dear students, in this second part, we will see what do we mean by semiconductor. And then in that we will see the types of semiconductor like intrinsic, extrinsic, and further in extrinsic we will see what is p-type semiconductor and what is n-type semiconductor. Okay, so in the last class we have differentiated between insulator, conductor and semiconductor, and now our flow will concentrate only on semiconductors. Okay, so here in this presentation today we will see about semiconductors. So here if you see the flow in which we are going to go today is, first we will see the basic definition of semiconductor. So the basic definition will always say that the resistivity of semiconductor lies between insulator and conductor. Okay, then second point we'll see classification of semiconductor, in which we will classify them as intrinsic and extrinsic, where intrinsic will be a pure semiconductor and extrinsic will be a impure semiconductor. Okay, then coming to the further classification, again we will classify extrinsic, that is impure semiconductor, into p-type and n-type semiconductor by adding some impurity. Okay, now what all these concepts are, one by one we will see. This flow is very easy, and our aim in this explanation today will be that we should understand what is p-type semiconductor, what is n-type semiconductor, because by taking both of these p-type and n-type semiconductors we are going to build the various semiconductor devices. Okay, so these are the basic building blocks. Clear? So first we will start with the definition of semiconductor. So here a simple definition of semiconductor says that it is a substance whose resistivity lies between conductors and insulators. Now when we speak about resistivity or when we speak about resistance, resistance means opposition to the flow of charge carriers, opposition to the flow of current, opposition to the flow of charge carriers like electrons or holes. Okay, what are those electrons and holes also we'll see afterwards, but at present you just remember that the opposition given by that particular substance to the flow of current lies between conductor and insulator. Means it will act as insulator also at some stage, and it can act as conductor also in some stage. Its resistivity lies between conductors and insulators. So here we always say that at lower temperature a semiconductor behaves as an insulator, and at higher temperature it behaves as conductor. Okay, that means it is having this flexibility that it can allow the current to flow also at some stage, and it can not allow the current to flow at some stage. And this flexibility makes it very popular to be used as a building block for electronic devices. Okay, now the most common semiconductor materials what we see in today's world, by which most of the electronic components are made of, they are silicon. Silicon is largely used, and the second one is germanium. So silicon and the germanium are the most commonly used semiconductors. Now at this stage now we know a basic definition of semiconductor, and we know examples of semiconductor like silicon and germanium. Now next we will go to see some other properties of semiconductor apart from this basic definition. So here you can see the first one is the same as we have told in the basic definition. Semiconductors have the resistivity which is less than insulators and more than conductors. Resistivity means we are speaking about resistance which lies between insulators and conductors, means it can also allow a current to flow like conductor. It can also does not support the flow of current like insulator. So it can behave as both. So its resistivity lies between both insulator and conductor, and that is the main feature because of which these semiconductor materials have become very important in many applications. Second one is semiconductors have negative temperature coefficient. Negative temperature coefficient means if the temperature increases, resistance has to decrease, and if the temperature decreases, resistance have to increase. So there is a inverse relationship between temperature and the resistance of that material. So again, we are speaking about the same thing. Resistance will increase and decrease. So here, the resistance in semiconductor increases with a decrease in temperature, and it will decrease with increase in temperature. That is vice versa. Okay, that means if the temperature increases, resistance decreases, means more current will flow. And if temperature decreases, resistance increases, that means less current will flow. Okay, so again, we are again speaking about that semiconductor can behave as insulator or conductor. Okay, then in the third point, the conducting properties of a semiconductor changes. Okay, the conducting properties of semiconductor changes means the ability of that semiconducting materials to allow a current to flow. The ability of the semiconducting material to allow a current to flow is called as conducting property. Now that can be changed, okay, when a suitable metallic impurity is added to it, which is very important property. Now this is where we are going to see, or this is where we are going to differentiate what is a pure semiconductor, that is intrinsic semiconductor, and what is impure semiconductor, that is extrinsic semiconductor. This sentence where we have said that when a suitable metallic impurity is added, okay, so when a metallic impurity is added, we can increase the conducting ability of semiconductor. We can increase its ability to make current flow through it. It can behave as a conductor. A charge carrier can flow through it. Okay, when a suitable metallic impurity is added. Okay, so there we come to a concept of classification of semiconductor, where we can say the pure semiconductor is intrinsic semiconductor, and the impure, where the impurity is added, okay, a suitable impurity is added, that it is called as extrinsic semiconductor. Then here, as we have told earlier, we will see the classification. So this is your basic semiconducting materials, what we have said first, the basic semiconductors. It can be classified into two. One is called as intrinsic semiconductor, that is your pure semiconductor. Pure semiconductor. So here you can give examples of germanium, you can give example of silicon. These are your intrinsic semiconductor. Okay, now there is a basic problem or basic drawback with this intrinsic semiconductor is that at room temperature, that at normal temperature, okay, it will not support flow of current. It will not allow a charge carriers easily to flow. Okay, so that is its a conducting property is less, its conductivity is less. So that is the case in pure semiconductor or intrinsic semiconductor. And that is why what we do is we add some impurity to this pure semiconductor. That means we add an impurity to this intrinsic semiconductor, and once we add that impurity in a suitable manner, that particular intrinsic semiconductor with impurity, if you see, then it will be called as extrinsic semiconductor. Now this extrinsic semiconductor is nothing but impure semiconductor. Now here we are making a facility. Here we are making the semiconducting material able to make a flow of current. So here it is having a facility where a charge carrier can flow because of addition of this impurity. Okay, now depending upon what impurity we are adding, depending upon after adding that impurity what major charge carrier we get, okay, now there we have a concept of electrons and holes that we will see in our next part. So based on that, we can classify this impure semiconductor, that is extrinsic semiconductor, as p-type semiconductor and n-type semiconductor. Now here comes the concept of p-type semiconductor and n-type semiconductor. And this p and n will allow you to make various electronic semiconductor devices. Okay, that is various electronic devices are made by taking this p and n type of semiconductors. That is why this basic study is important. Okay, now till here it's very easy, the flow. That is, what is semiconductor? A semiconductor is a material whose resistivity lies between conductors and insulators. The basic examples are germanium and silicon. Then there can be two types. Basically, one is intrinsic, which is called as pure semiconductor, whose conducting property is very less, our conductivity ability is less. Then if you add impurity, it becomes an extrinsic semiconductor, in which, depending upon what kind of impurity we add, we can have p-type semiconductor and n-type semiconductor. Okay. Now, to understand this p-type semiconductor and n-type semiconductor, to understand what is this impurity added to intrinsic semiconductor, to understand what is this extrinsic semiconductor, we should again come back to a concept of what were our valence electrons when we spoke about atomic structure. And after we know what are valence electrons, what are covalent bonds? Okay. And after we know what are covalent bonds, how does this covalent bond break, or how does it produce a charge carrier like electron or holes? Then in that concept, what is electron and what is hole? This is what you have to understand here. Because if you understand this, then it is very easy to understand the basics of p-type and n-type semiconductor. And we want to reach that p-type n-type semiconductor because those are the basic building blocks of all our electronic semiconducting materials. Clear? So now again we will go to see the atomic structure. We will see the valence electron. We will see what is covalent bonds, and then we will see how do the charge carriers are made free so that they can help for the current to flow in the semiconductor. Then here we will see first the definition of intrinsic semiconductor, and then we will go to see the atomic structure and the covalent bonds. Okay, so as a theory, as we have already spoken about this, intrinsic semiconductor, pure semiconductors are called as intrinsic semiconductors. Silicon and germanium are the most common examples of intrinsic semiconductors. Both these semiconductors are most frequently used in manufacturing transistors, diodes, and other electronic components. Intrinsic semiconductor is also called as undoped semiconductor because it is not added with impurity. So adding impurity is called as doping method. So now intrinsic is pure semiconductor, so it is called as undoped, or it is called as I-type semiconductor. Okay, so only basic thing what you have to remember is pure semiconductor is called as intrinsic semiconductor. Then we will see the atomic structure of silicon atom and germanium atom. So here you can see the first one, what we have shown is silicon atom. This is silicon atom. Now silicon atom has a central nucleus, and around the nucleus you have orbits, and in that orbits you have electrons, and in silicon there are around 14 electrons. Okay, now how these 14 electrons are distributed? So here you can see in the first orbit you have 2 electrons. This is number 1, this is number 2. In the second you can have maximum 8 electrons according to the theory of atomic structure. So here you can see 8, 1, 2, 3, 4, 5, 6, 7, 8. So 2 plus 8 is 10, then 14 means another 4 will remain, and in the last orbit you have these 4 electrons. This is 1, 2, 3 and 4. So these 4 electrons in the last orbit are called as valence electrons. Okay, and now this same atomic structure only with respect to valence electron, you can show it like this. This is your silicon atom. Okay, and then here you can have a valence electron, here you can have a valence electron, here you can have a valence electron, and here you can have a valence electron. This is how you can show for silicon. Similarly, if you see germanium, germanium atom will have 32 electrons. Germanium will have 32 electrons. So 32 electrons, okay, in the orbit around the nucleus. So here again we'll see the first orbit will have 2 electrons, second orbit will have 8 electrons. So 2 plus 8 is 10. So maximum second orbit can have 8 electrons. So 2 plus 8 is 10. Then the third orbit maximum can have 18 electrons. So here you can see 18 electrons in the third orbit. So 2 plus 8 plus 18, that is 2 plus 8 is 10 plus 18 is 28. Then for 32 another 4 will remain, and that 4 will be in the last orbit. So here you can see this is 1, this is 2, this is 3, and this is 4. So these 4 are your valence electrons. So the electrons in the outermost orbit, as we have seen in the atomic structure, are called as valence electrons. Now here also you can see, if you want to draw a germanium atom only with valence electrons pattern, then you can see this is germanium, and here you can show one valence electron, here you can show another valence electron, here you can show another valence electrons, and here you can show another valence electrons. Now both the silicon and germanium has 4 valence electrons, and that's why they are called as tetravalent elements. Tetravalent means they will be having 4 valence electrons. Okay. Now whenever we have a crystal, whenever we have a silicon material in which we have many silicon atoms, or whenever we have a germanium material and there are many germanium atoms, then the atoms we can show it like this. That is, say this is one silicon atom. Okay, so there will be a valence electron here, there will be a valence electron here, there will be a valence electron here, and there will be a valence electron here. Now if there is another silicon atom adjacent to that, then the valence electron of that silicon atom will make a bonding with the valence electron of the earlier silicon atom. Similarly here, and similarly here. Okay, so like this bondings will take place. Again you can have a silicon atom here, here it will have its valence electron. Again you can see you can have a valence electron here, you can have a valence electron here, you can have a valence electron here. Again you can see that the 2 valence electrons of the 2 atoms are making a bond. There is a bonding, and this bonding is called as covalent bonding. Same thing will happen along with germanium atoms also. Clear? So here we come to a concept which is called as covalent bond. Now these bonds which are made by the adjacent atom valence electrons, so 2 valence electrons will combine with each other to make a bonding, and that bonding will be called as covalent bond. Okay, now that covalent bond is very important, because at a certain higher temperature, or if a temperature increases, one of the electron can break the bond and come out. So if an electron comes out, it becomes a free electron which will help you in the flow of current, and the empty place of that electron, what is there in that bond, will be called as a hole, and there you can have a concept of a positive charge particle. Clear? So then we come to a concept now to know what are electrons and holes. Okay, now first we will see what are these covalent bonds, and then we will see this structure, and we'll see how these valence electrons are going to make the covalent bonds. Here you can see there is a image shown where silicon atom is shown, and the valence electrons are shared by every atom. So these all are atom. This is one atom, this is second atom, this is third atom, fourth atom. Okay, so all these are there, and you can see this valence electrons are shared. These are making bonds, these are covalent bonds. Okay, so these valence electrons of adjacent atoms are shared, these valence electrons are shared. So these are bonds, these are bonds which are called as covalent bonds. These are covalent bonds. Okay, so that is covalent. Valent means it's speaking about valence electrons. So here if you go to see the definition of covalent bond, the outermost shell has the valence electrons which are loosely attached to the nucleus. Such an atom having valence electrons, when brought close to the other atom, the valence electrons of both these atoms combine to form electron pairs. This bonding is called as covalent bond. Okay, now after we know this concept of covalent bond, then we should know the concept of what are free electrons and what are holes, and that simultaneously will take you to the concept of converting intrinsic semiconductor into extrinsic semiconductor by adding impurity, because at room temperature you cannot do it much, You have to add impurity so that the conducting property of the semiconducting material will increase. Its ability to make the current to flow will improve. Okay. So then, as an example, we have seen earlier also that germanium atom will take here, and in that we can speak about covalent bond. So for example, a germanium atom has 32 electrons, 2 electrons in the first orbit, 8 in the second orbit, 18 in the third orbit, and 4 in the last orbit. So these 4 electrons are valence electrons of germanium atom. These electrons tend to combine with valence electrons of adjoining atoms to form the electron pair, and as we have seen earlier, this will be the pattern of that, where you can see germanium atoms and therefore 4 valence electrons making covalent bonds. Okay, same thing we can show for silicon atoms. Then we will come to a concept of what is a hole, H-O-L-E, because whenever there is a covalent bond, say for example we show here, there is a atom, say silicon atom or germanium atom, anything you can take. There is a atom, silicon atom or germanium atom, and then its valence electron, one of its valence electron is making a covalent bond with the valence electrons of other atoms. So here is the covalent bond. Now if the temperature increases, this covalent bond can break, and if it breaks, this electron can come out and become a free electron, where that free electron can be used for the flow of current. And the place remaining, that is the absent place of that free electron, will become a hole. This is a hole which can be considered as a positive charge. Okay. Now this can happen when the temperature increases, but at room temperature it is not so easy for a semiconductor material to have this type of ability. Therefore we go to add some impurity, because these covalent bonds can be broken, and then we can increase either the number of electrons or we can increase either the number of holes, and then we can define what are p-type and n-type semiconductors in our extrinsic semiconductor. Okay, now at present we will see this definition for hole. A creation of hole, how it is created: due to the thermal energy supplied to the crystal, some electrons tend to move out of their place and break the covalent bond. Okay, the covalent bond of 2 valence electrons will break. These broken covalent bonds results in free electrons which wander randomly. They become free and they come out. They should be properly used for a flow of current. But the moved away electron creates an empty space in the valence behind. So as I've shown on top, there is an empty space when one electron goes out, and that empty space we can take it, or we can call it as a hole, and we can assume it as a positive charge. This hole, which represents a missing electron, can be considered as a unit of positive charge. It will be considered as a unit of positive charge, okay? While the electron is considered as a unit of negative charge. The liberated electrons move randomly, but when some external electric field is applied, these electrons move in opposite direction to the applied field. But the holes created due to the absence of electrons move in the direction of applied field. Because now here we are going to say that when electrons can move in one direction, similarly if you speak about holes, holes will move in the opposite direction of electrons. Electrons are negative charge particles and holes are considered as positive charge particles. Then what are the properties of intrinsic semiconductors? So the intrinsic semiconductor properties are: the electrons and holes are solely created by thermal excitation. Now intrinsic semiconductor is a pure semiconductor, so we have not added any impurity. So the number of holes and electrons which are created only by increasing temperature, that's all. If the thermal excitation is there, holes and electrons can be created, but those are not enough for a conductivity, for a phenomena of conduction, for a phenomena of flow of current. Second, the number of free electrons is equal to the number of holes. Third, the conduction capability is small at room temperature. This is very important. This is the need why we are going then from intrinsic to extrinsic. Then fourth point, you see, in order to increase the conduction capability of intrinsic semiconductor, it is better to add some impurities. Now here we are speaking about some impurities. What are the specific impurities, and after adding that impurity, what happens to intrinsic semiconductor, we will see. Now the process of adding this impurity is called as doping. This is one of the important phenomena, because we cannot depend here at only temperature, because at room temperature it is not going to give us a correct conductivity property of semiconductor. Its conductivity capability is very small at room temperature. Therefore, to make this material to have a proper flow of current at room temperature, we will go to a method called as adding some impurity to it. So by adding impurity, we can either increase the electrons in that structure, in that crystal, or we can increase the holes in the structure in that crystal. Okay, and therefore we'll have some more charge carriers for the current to flow. Then, as I've told you earlier also, doping, it is the process of adding impurities to the semiconductor material, and that is called as doping. The impurities added are generally pentavalent and trivalent impurities. Now here comes the concept of pentavalent, means you are having 5 valence electrons, materials which are having 5 valence electrons. So this is pentavalent. These materials will have 5 valence electrons, that is 5 electrons are there in the outermost orbit. And trivalent means 3 valence electrons, that means it will be having 3 electrons in its outermost orbit. These are important because if you add a pentavalent impurity to a pure semiconductor, that is intrinsic semiconductor, it will become extrinsic semiconductor. But in that extrinsic semiconductor also, it will become a N-type semiconductor. Similarly, if you add a trivalent impurity, it will become a P-type semiconductor. Now, how this happens, we will see. Pentavalent impurity. The pentavalent impurities are the ones which has 5 valence electrons in the outermost orbit. Example of these materials are bismuth, antimony, arsenic, phosphorus. The pentavalent atom is called as a donor atom because it is going to give you one extra electron. Afterwards, we'll see that, because it donates 1 electron to the conduction band of pure semiconductor atom. Okay, then a trivalent impurity definition, if you see, the trivalent impurities are the ones which has 3 valence electrons in the outermost orbit. So example of these materials are gallium, indium, aluminium, and boron. The trivalent atom is called as an acceptor atom because it accepts 1 electron from the semiconductor atom, and it will give you it will give you more number of holes. Okay, then after knowing all this, what is doping, okay, what are these impurities, what is pentavalent impurity, what is trivalent impurity, then we can come to this concept of what is extrinsic semiconductor. Now, why we are coming to this stage of extrinsic semiconductor? Because when we had this pure semiconductor, that is intrinsic semiconductor, its capability of having a current to flow through it is very less at room temperature, and that is not useful for us in any application. That is why now we have come to a stage where we want to add some impurity to this pure semiconductor so that it becomes extrinsic semiconductor, and depending upon the type of impurity, we can have N-type semiconductor or P-type semiconductor. So here if you see the definition, an impure semiconductor which is formed by doping a pure semiconductor is called as extrinsic semiconductor. Now I think you know the difference between intrinsic and extrinsic. There are 2 types of extrinsic semiconductors depending upon the type of impurity added. They are, if you add a pentavalent impurity, you get an N-type extrinsic semiconductor. If you add a trivalent impurity, you get a P-type extrinsic semiconductor. Then coming to the definition of N-type extrinsic semiconductor, a small amount of pentavalent impurity. Pentavalent means 5 valence electrons material. A small amount of pentavalent impurity is added to a pure semiconductor to result in N-type extrinsic semiconductor. The added impurity has 5 valence electrons. For example, if arsenic atom is added to the germanium atom, 4 of the valence electrons get attached with germanium atom, while 1 electron remains as a free electron. Okay, so this is a concept where we can generate more number of extra free electrons by adding this impurity, and because of that, this type of material where we add pentavalent impurity is called as N-type semiconductor because there are more number of electrons in that. So here you can see arsenic atom is shown here. Now arsenic atom is a pentavalent impurity, so it will be having 1 valence electron, 2 valence electron, 3 valence electron, 4 valence electron, and you will be also having a 5th valence electron. Now here what will happen is the 4 valence electrons, if you add this arsenic with germanium or silicon, now the 4 valence electrons of the germanium or silicon will make covalent bond with the 4 valence electrons of arsenic. So here you can see this is a covalent bond between the valence electrons of germanium and arsenic. This is covalent bond, this is covalent bond, this is covalent bond. Now germanium is having 4 valence electrons, but arsenic is having 5 valence electrons. So 1 electron will remain extra. Now that electron which remains extra is called as free electron. And if you add a small amount of arsenic impurity to this germanium or silicon, you can produce many such free electrons. So there will be a large number of free electrons which will help you to make a flow of charge carrier electrons, and that is the flow of current. And because there are more number of free electrons, and because the electrons are negative charge particles, this type of semiconductor where you're going to add a pentavalent impurity is called as N-type semiconductor. So here you can see all of these free electrons constitute electron current, hence impurity when added to pure semiconductor provides electrons for conduction. In N-type extrinsic semiconductor, as the conduction takes place through electrons, the electrons are majority carriers and the holes. Now here we are speaking about electrons are majority carriers which are made because of doping by adding impurity. But because of temperature also some covalent bonds will break, and then some holes also will be produced, and those will be called as minority charge carriers. So in an N-type semiconductor, we can again have a concept of majority charge carriers and minority charge carriers. Because of doping, you will get electrons as majority charge carriers, moreover, and because of temperature, you can get holes, few holes also you can produce, which are minority charge carriers. When an electric field is applied to N-type semiconductor, the free electrons, which are the majority charge carriers, travel towards the positive electrode. This is called as negative or N-type conductivity. So here if you say you are having a N-type semiconductor, this is your N-type semiconductor in which the majority charge carriers are electrons. These are electrons. Okay, now here if you apply it to an electric field, say if you apply it to the battery here, now this will be a battery in which you will be having this positive terminal and negative terminal. Now these electrons here in the N-type semiconductor are negative charge particles, and if you see this battery will have a positive terminal here. So these electrons will be attracted towards this positive terminal. Okay, and this negative terminal will repel the electrons from here to move ahead. Okay, so that is how the electrons will flow now in this direction because of the battery whatever you have connected to this N-type semiconductor. Then we'll come to see what is P-type semiconductor. A small amount of trivalent impurity if we add to pure semiconductor, it will be a P-type extrinsic semiconductor. The added impurity has 3 valence electrons. For example, if boron is added to germanium atom, 3 of the valence electrons get attached with the germanium atom to form 3 covalent bonds. But 1 more electron in the germanium atom remains without forming a bond, as there is no electron in the boron remaining to form a covalent bond. That empty space where there is no electron is treated as a hole. So here you can see we have a boron atom here. Boron is a trivalent atom, so it will show its 3 valence electrons, 1, 2 and 3. There is no 4th valence electron. It is a trivalent. Now you are going to add this impurity to germanium or silicon, which are tetravalent, which has 4 valence electrons. So here you can see germanium will have 4 valence electrons, or you can also take silicon here. They will be having 4 valence electrons. Now these 4 valence electrons, and the boron has 3 valence electrons. So out of these 4, 3 will make covalent bonds. As you can see here, this is a bond, this is a bond, this is a bond. 3 valence electrons will make covalent bond, but the 4th electron of germanium will not have an electron from boron to make a covalent bond. So here you see there is existing an absent place of electron, and that is considered as hole. That is considered as hole. So if you add a small amount of trivalent impurity to the intrinsic semiconductor like germanium or silicon, you can produce many such holes. and here the holes will become the majority charge carriers, and these are positive charge, are considered as positive charge, and that is why this combination, when you add this trivalent impurity, is called as p-type semiconductor. So the boron impurity, when added in a small amount, provides the number of holes which helps in the conduction. All of these holes constitute hole current. In p-type extrinsic semiconductor, as the conduction takes place through holes, the holes are majority carriers while the electrons are minority carriers. Now here in p-type extrinsic semiconductor, because of the adding of impurity, because of the doping process, we are going to produce majority carriers as holes. And because of temperature excitation, there are few covalent bonds which are broken, and because of that some free electrons also can arise. So here majority charge carriers which are constituting the flow of current are holes, and minority charge carriers are electrons. The impurity added here provides holes which are called as acceptors because they accept electrons from the germanium atom. When an electric field is applied to p-type semiconductor to which trivalent impurity is added, the holes travel towards the negative electrode. This is called p-type conductivity. In this p-type conductivity, the valence electrons move from one covalent bond, unlike the one covalent bond to another, unlike the n-type semiconductor. Now here simple thing what you have to remember is, say if you are having a p-type semiconductor, this is p-type semiconductor in which the majority charge carriers are holes. These are holes. Now here if you connect a battery and the battery is having a positive terminal here and negative terminal here, okay, now the holes are considered as positive charge, so they will be attracted toward the negative terminal of the battery, and the positive terminal of the battery will repel these holes. That means the holes are going to move in this way for this type of battery connection. Okay, thank you students.